Chapter 20, slides 33 to 35. The amide is the last carbonyl derivative of carboxylic acids that we're going to discuss in this chapter. And as mentioned in the reactivity sequence, amides are the least reactive derivative of carboxylic acids. So from a carbonyl perspective, the carbon of the carbonyl is not very reactive. There's your amide. And amides play a very, very important role biologically because they constitute proteins, right? So the entire group here, this whole group, the carbonyl with the nitrogen off right flanking it, is an amide. Specifically, the bond between the carbon and the nitrogen is referred to as the peptide bond. So the peptide bond, multiple amino acids that come together to form peptide bonds, form long chains called peptides. So you'll notice that we start with a carboxylic acid, the amino acid, the amine of another amino acid. I'll use a different color sequence here. So if I color two amino acids, so here's an amino carboxylic acid, amino acid, and let's say I have a different amino carboxylic acid. The nitrogen of the amine from one amino acid can do an in, up, down, out reaction with the carboxylic acid of the other amino acid. So one end of the molecule is reacting with the other end of a different molecule that are very similar. And this new bond where the nitrogen exchanges for the OH through a 1,2 substitution in the same mechanistic format that we've just seen is where we end up forming these peptide bonds, the amide bond. So a very, very important reaction in biochemistry. And you can see all of these peptide bonds or amide bonds in the carbon chain sequence for the protein down below. So amino acids, many of them come together to form these peptide bonds, which form peptides. And then peptides end up folding into proteins using intermolecular forces, right? Because of the intermolecular forces, what one end of the molecule is attracted to another end, you either form these beta-pleated sheets or cyclical, right, helical type formations of these long chains. And so you end up getting these secondary and eventually tertiary structures for the molecule as these very macro molecules have conformations that are stable. Now, we see amides in smaller molecules too, like inorganic. One of my favorites is the one found here in chocolate. It's only in small amounts, but anandamide is a fatty acid neurotransmitter derived from non-oxidative metabolism. And what's interesting is that this compound's been found to bind to the same receptor in the brain as does THC. Which is the active ingredient in marijuana, as many of you know. So my public service announcement is eat chocolate. Okay, well, we're only going to cover a couple reactions because if you'll notice, a lot of the chemistry of amides we've already covered. Because these 1,2 substitution reactions, many of them tend to be reversible. If what you're putting on is something that could be taken off just as easily. A nitrogen exchanging for an oxygen exchanging for another oxygen, an oxygen exchanging for a nitrogen, a chlorine exchanging for an oxygen, right? That was not reversible. But for many of them, oxygen for oxygen, nitrogen for oxygen, oxygen for nitrogen, these are interchangeable. Thus, they are in equilibrium. Think about the nucleophile you're adding. It'll very easily tell you whether you're using equilibrium arrows or unidirectional arrows. So I'm just going to go through a formal 1-2 substitution where we're going to start with some amide. And we could do a methylamide under acid catalysis because they're so weak. They're not very reactive carbonyl-wise, which again is a good thing. Otherwise, our proteins would be collapsing all over the place, falling apart and reacting with all sorts of nucleophiles. We need acid-base chemistry first to get these carbonyls activated. We've seen that with the esters as well. Now that the carbonyl is more reactive, the weak nucleophile, in this case water, this is hydrolysis again, right? Hydrolysis, acid and water. Now we're going to do our in-up. I'm under acid catalysis. I don't want to come down and out until I make the leaving group, something that is okay leaving. So what I'm doing is I'm putting on the water. I'm driving the water on. I'm going to drive the nitrogen off. So before I do that, I want the nitrogen to leave in a neutral state. So we're going to do a proton transfer. This is purely for electron pushing on paper. Understand that in the media, there's protons everywhere. So the protons are going to be wherever you need them to be. But we like to write this step out. Now we can do our down and out. Our carbonyl remains protonated because I am still in acidic media. And I've lost the amine. The amine itself could probably deprotonate the proton from the carbonyl, but I'm just going to add a workup here to neutralize everything so that the acid-base chemistry can occur, neutralizing, plucking off that extra proton and revealing my carboxylic acid. So I've replaced the nitrogen for an oxygen. In, up, down, out again. So amides behave the same way. If you go back and look at all of our previous reactions, we've made amides, right, from esters. So you can do all of those by interchange. There's only one reaction that is tricky. And this is the only other one I'm going to cover on the amides because 1-2 substitution reactions, you're getting the hang of them now. They're very repetitive. And so this is the only one that is going to trip you up. You might go, well, I've seen hydrides before, and you absolutely have. The key here is the fact that these reactions are not reversible. Unidirectional arrow, because what you're putting on cannot be taken off, like the Grignards or the hydrides. We've got a hydride. We're going to shorthand lithium aluminum hydride is 4 equivalents of H-. So there's tons of H- in here. We're working under strong basic nucleophilic conditions. We don't need to catalyze anything. It's already very strong. And so it's going to do in up. So far, so good. Why is this tricky? The reason this is tricky is because this is not an equilibrium reaction. And so effectively, what's going to occur is that, remember how I said the oxygen is attracted to the aluminum? Yeah, well, this is coming back to haunt us. Okay, so it's going to release some more H-, but that oxygen really does not want to let go. You are not going to allow this oxygen to come down. Now, you might go back and look at the ester converting, reducing. There was always another oxygen around for the aluminum to form bonds with. And so there were lots of different ways that we could continue to reduce our system. Here, we've got one shot. Again, it's unidirectional. And so the nitrogen being, nitrogen, less electronegative, much more generous, less greedy with its electrons, it's the one that actually does the down out. And this is the tricky step. It's the nitrogen, because I've only got one shot to do this. The down out happens with the nitrogen. Okay, so that is your tricky step right in here. So what does that get us? It gets us a very funky looking system, which we haven't learned about yet, but you will in second semester organic. So I just want you to think about this as a carbonyl. Remember when you had carbonyls and they had protons on them, they were activated? This is like a nitrogen version of that. It's like a carbonyl that's activated because it's got a nitrogen on it. So let me just track. Carbon 1, carbon 2, carbon 1, carbon 2. The nitrogen formed a double bond between itself and carbon 2. The oxygen went away with the aluminum, which was fine. It kept its aluminum-oxygen bond. And we formed this iminium species, which you'll learn about more next semester. But no matter, it's just like its cousin, the carbonyl, the activated carbonyl, and it is an activated carbon electrophile. And we've got lots of H minuses still floating around, so we're just going to do one more H minus in up. In and up. So at the end of the day, let's track it. The first H minus went in and up. There it is. It's on carbon 2. And then the nitrogen pokes in and out. So the down out happens, but with a very different tricky sequence. It's not the O minus that does the down out. It's the nitrogen that does the down out. Okay, so we had, to this point, only had added the one hydrogen. And now we're just going to continue on and add a second hydrogen. So we've added 2 hydrogens to the carbon, reducing it. There's no longer a double bond between carbon 2 and the nitrogen. And after workup, you end with this amine. And in the next semester, this is going to be one way that you can convert amides, which are neutral, to amines, which are basic. So you just got to slow down on this mechanism, because if you end up doing the in, up, down, out, and you use the oxygen to kick off the nitrogen, you are not going to come up with, as an answer, the amine as your product.